Okay, so good afternoon, everyone. Welcome back to this live problem solving session for the week 2 of the course Essentials of Topology. So, I am Siddhartha Pramanik. I am a PhD student at the Department of Mathematics, IIT Kharagpur. So, uh, I am supposed to solve some problems based on the contents of the second week. But before, if you people have any doubts from the lectures, just feel free to ask. You can just unmute yourself and ask, or you can put it in the chat box also.
Sir, in the last class, one question, d1 upon 1 plus d2, d1 and d2 are two different matrices.
Yeah,
Then d1 upon 1 plus d2, is it a metric or not? You have asked, sir. That I am
yeah.
not getting.
So have you tried?
Yes, sir, I tried, but where it will fail, I thought it will be in triangular inequality. Maybe.
Yeah.
But it,
So the first two axioms will hold. The only problematic part is the triangle inequality. So I I think it will not be a metric, and you will get some counter example. But at this moment I don't have the example, so maybe you can try artificially by constructing some metric, or maybe I will let you know sometime, or if I forgot, you just put it in the discussion forum so that I I can see it once again.
okay, sir. Thank you.
Yeah, okay. Anything else? Yeah, any other doubts from the lectures? Okay, so you can ask anytime during the session. That is not an issue. So maybe I will start. So first I will just briefly write down the topics of this second week. Then I will come to the problems. So in the first week we end up with the definition of a topology and two or three examples. And in the second week we looked at couple of examples. So various examples of topologies like cofinite topology, co-countable topology, and particular point topology, excluded point topology, those things. And particularly we have defined two topologies on the set of all natural numbers. Maybe I will put it here. So some topologies on set of all natural numbers, the initial segment topology or final segment topology, and some topologies on the real numbers. Okay. Then we started comparing these topologies. So comparison of topologies, basically which one is finer and which one is coarser, or in other words, which one is smaller or which one is bigger, and particularly comparison on topologies of R. Comparison of topologies on the set of all real numbers. After that, we have seen when union is a topology or intersection is a topology. So we have seen that intersection of any collection of topology is again a topology, but union may not be a topology. So maybe I will put it here. And after that, we have defined closed sets, so which are basically complement of open sets. And we have seen couple of examples and properties of these things. And in the end of week 2, we have defined what do we call by basis of a topology. Okay, so these are the more or less the topics of the second week. So if you have any doubt or if you have any question, just uh, put it in the chat box or unmute yourself and ask. Okay, maybe I will start solving some problems. By the way, any one of you have registered for the exam of this course?
Sir, not yet. Still, the last date will be around August 8th or 5th.
Okay, fine.
For
No
that reason.
issues. Okay, so the first will be registered. Okay, great. That's good. Yeah, if you give the exam, then only you will be you will take this course to some extent seriously. So first problem is from GATE 2009. So uh, let me define two collection of subsets. So first one is all those subsets of R such that either G is finite or G complement in R is finite. And the second one is all those subsets of R such that either G is countable or G complement is countable. Okay, then basically we have to say which one is a topology or which one is not. So then the first option is neither tau 1 nor tau 2 is a topology. Second option is tau 1 is a topology but tau 2 is not. Third one is the other way. So maybe I will just copy. So tau2 is a topology and tau1 is not a topology. And the last one is both tau1, tau2 are topologies. Okay, so the question is very simple. We have the base set is set of all real numbers, and we have two collections tau1, tau2. Both are subset of our set of R. We need to check which one is a topology and which one is not. So let's start with the first one, this tau1. So all those subsets of R which are either finite or whose complement is finite. So is it a topology on R? Try to think. So we have to check three axioms for the topology, right? So maybe I will write the axioms here. So the first one is the empty set and the whole set belongs to tau. Second axiom is closed under finite intersection. So I will just write finite intersection. And arbitrary union, closed under arbitrary union. So just check these three axioms one by one for the first one, for tau1. Yes, any guesses or any answers?
Sir, it is not closed under unions.
The first one.
Yes.
So, do you have any particular example?
Yes, sir. If we union over the natural numbers, the singleton set I,
Yes,
then uh, all those singleton set I are finite, so they are
yes,
in
yes, you are right.
tau.
Yeah, exactly. So,
But
so tau1 is not a topology. So, try to think about the second one. So, tau1 is not a topology on R because uh, so for all natural number n, if you take the singleton set n, this is a finite set. So this is belongs to tau1. But if you take the arbitrary union of the singleton sets, this is natural number. So this is does not belongs to tau1. So it is not closed under arbitrary union. Is not closed under arbitrary union. So tau1 cannot be a topology on R. Now what about the second one? So the similar kind of argument I think will not hold, but try to think what will happen for this. So is it a topology on R tau 2? So any guess? Okay. So see, what is tau 2? Those subsets which are either countable or whose complement is countable. So so for the first one, we have constructed a set whose arbitrary union is not in the topology or not in that collection. So just try to use the similar kind of idea. So note that. Any singleton set will be in that collection. So for all x belongs to the real number, uh, if you take the singleton set, then it is a finite set, so it is a countable set. So it indeed belongs to tau 2. But if we take, let's say, uncountable set, let's say open interval 0, 1, we know this is uncountable, right? And this is exactly equals to union of singleton set x, where x belongs to open interval 0, 1. But this is not in tau 2 because this is neither countable and its complement is also not countable. So this is also not closed under arbitrary union. So this is also not a topology. Is it okay? Did you get my point? So the correct answer is the first one. Neither tau 1 and not tau 2 is a topology. Any questions?
So I have another example.
Sorry,
So I have another example of for tau 2.
which
So
one?
for tau 2,
For tau 2?
so if we take the set of r minus q irrational numbers, then r minus q should be in tau 2 because the complement is rational number, so that is countable.
R minus q is in tau 2, yes.
And set of rational numbers q is also in tau 2 because it is countable. So, but
Yeah,
if we take the union of these two sets, that would be the set of real numbers, and that is not countable. So that is
R
also
is
another.
not countable, but R complement is countable. That is a finite empty set. Empty set is finite.
Okay.
Yeah, so you cannot argue in that way. But did you understand this example?
Yes, sir.
Yeah, okay.
So even in place of 0, 1, can we take R means
Can we take
singleton R arbitrary union X belongs to R.
uh, instead of the open interval, what you want to
R
take?
R real line.
But real set of all real numbers is in tau, right? Because
But
R,
those subsets we have to take, it should complement should be countable or set should be countable.
yes. So R complement is empty set, that is countable.
Okay, sir.
Yeah. Okay, maybe is there any other questions regarding this? Okay, then let's move on to the second problem. So this is from GATE 2006. So recall from the lectures that on R we have the usual topology and we denote it by tau e. Euclidean topology on R, that is the usual topology, that is coming from the metric defined in this way, right? So we will need this in this problem. So consider the the topological space. Okay, consider the usual topology. So okay, so for convenience I am writing it tau e on R. Okay, so this is the usual topology coming from the metric. Now define. So I will define two more collections. So first one is all those subsets of R such that you, okay, maybe it is just union of phi in the whole set R and this collection. So I have to modify this. So U is so U belongs to tau E and U is bounded. So from real analysis we know when a subset is bounded, subset of R is bounded. So it is in that sense. And T is phi R and all those subsets U, subsets of R such that U belongs to tau E and U is unbounded. So we have two collections. Again, we have to check which one is a topology and which one is not. Then the first one is S is a topology but T is not. S is a topology on R but T is not. T is a topology but S is not. Uh, both S and T are topologies on R. And the last one is neither T or nor S is a topology. So neither S nor T is a topology. Okay, so I hope you have understood the problem. So maybe you will write down the definition of bounded set here. So a set, let's say A subset of R is bounded if uh, there exist two real numbers, let's say A and B belongs to R such that A is subset of this open interval. Maybe this is not the actual definition, but you can take this as a definition for this time because both are equivalent.
Sir, neither S nor T is a topology.
Okay, but how?
Uh, for the first case, for S case, we can take the union over R of the open intervals 1I.
Uh, Open intervals?
1I.
One I.
Yes, union I and R.
Okay. Okay, then this will be 1 comma infinity. But this is not a bounded set. But this
Yes.
is, yes. So this is also not closed under arbitrary union. Okay,
Uh,
maybe. Yeah, so go ahead for the second one.
And for the second one, we can take the intersection of minus infinity to 2, union 1 to infinity, open.
Yes. So this will be close interval 1 to 2, and this is not in tau e.
Sir, it will be open 1 to 2, I think.
Is it? Yes. Yes, yes, yes. It is open. But that is not unbounded set. That is a bounded set. So neither is not T is a topology. So I hope others got this example. So maybe I will write down this quickly. So the answer is option B. So for S, so S is not a topology because uh, let's say one, okay, maybe let's say 0, because 0 to n belongs to S for all natural numbers, but their union. So if you take union of these intervals, then you will get 0 to infinity. So this is not in S. So this is not closed under arbitrary union. And for T, this is not closed under finite intersection. So you can take the same example, because minus infinity comma 2, this is an unbounded set, and 1 comma infinity, this is also an unbounded set. So both are in T, but their intersection this is open interval 1 2, this is not in T. Okay, so this is a very simple example. So I hope you have understood this. Is it okay, or is there any doubt? Okay. Okay, maybe then let's move on. So now I will introduce one important topology. This will be useful, and I will come to some questions. But I will 6:30. Okay, I can prove. So okay. So this is known as K topology. So let K be this set. It is 1 upon n, where n running over the natural numbers. Okay, now using this set, define. So I will define a topology on set of real numbers. So let's define this tau as all those subsets of R such that for all x belongs to G, there exist real numbers A, B in R with A less B, such that uh, either x belongs to this open interval and this is subset of G. So this is also we have seen in the usual topology, or If it is not true, then x belongs to this open interval AB minus k, and this is subset of G. Okay, so this is my definition of tau. Now, this tau will form a topology. It is not very difficult to check. I think in the upcoming lectures also you will see, but in a different way. So I will not prove that it is a topology. So I am just leaving it to you. And tau is a topology on R, and this is known as K topology. Okay, so just try to prove this. This is not difficult thing, just routine check. Okay, so let's spend few minutes on this to have some idea topology. So first of all, we will denote this topology. So we shall denote this topology by tau k, because it's a k topology. Okay, now let's deduce some properties, or let's see what kind of sets in this topology. So if you see this definition, then you can clearly see that these open intervals are elements of this tau k, right? So the first question is for AB belongs to R with let's say A less than B, whether the intervals let's say close interval AB, let's say open interval AB, and the semi open intervals belongs to tau k. Okay, so let's see this. So clearly open interval belongs to tau k, because from the definition itself it is clear. But what about the other kind of intervals? What do you think? So close intervals belongs to tau k. Is it possible? So this is the real line. This is the 0. This side is infinity. This side is minus infinity. Suppose you take a closed interval here. So when this interval belongs to tau k, if for every element of that interval we need to find some real numbers such that this condition or this condition holds. So for this closed interval, okay, so let's take closed interval 2 3. Then what can you say? Is it belongs to tau k? Just focus on the end points, because for open interval it is already there. So we need to focus on these end points 2 and 3. So see, 2 belongs to this closed interval, So for 2, can we find an open interval AB such that this is subset of this 2 comma 3? This is not true, right? Because we have seen in the usual topology case, this will not hold. But what about the other condition? Is it possible 2 belongs to some open interval AB and minus K that is subset of 2 comma 3?
No, sir.
Yeah. So what is our K? K is just 1 by n. So our K lies here 1, 1 by 2 and so on. So it is uh, outside the range of that set. So what do I mean that? Um, Maybe I'll just leave it to you to observe these things. This is not difficult. Uh, so similarly, these kind of things, if you focus, so these type of intervals are not in tau k. Okay, so you just have to observe the things, just sit with it, just stare at the definition, and you have to convince yourself. That's all. So now, what about other kind of sets? Whether finite sets, sets of natural numbers, Z, Q, R minus Q, these are elements of tau k or not? So what about finite sets? So for finite sets and n and for Z, you can give a similar argument that these are not belongs to tau k. Because what are our condition? So this kind of interval and this kind of interval minus k has to be inside that set. But this interval is an infinite set. In fact, it's an uncountable set. And this also an uncountable set because k is countable. So inside a finite set, can we have an uncountable set? No, right? Because these open intervals and open intervals minus k, these are infinite sets. So this cannot be subset of a finite set. And also this cannot be subset of n. So if you just look at this real line, if you take this point 1 and point 2, so now if you take an interval around this point, and if you then can this interval inside n? This cannot be inside n, right? Even if you subtract k from this set, this cannot be inside n. Now what about rationals and irrationals?
They will also not come since they are taken
Yes,
from any intervals.
they will also, they are also not member of tau k, and the reason is their density. So we have seen similar argument in the lectures for the usual topology. So inside q and inside r minus q, they cannot contain intervals. So I am leaving it to you. So but what kind of set it contains. But one important set it contains, you have to realize that. See, if you take this interval, open interval, and if you subtract k, then by definition, this is inside tau k. Okay, so this is an element of tau k. This will be important for us. Okay, so any questions so far? Okay, so there is no questions. Let's
Sir, is it comparable with any, just like lower
yeah,
limit
that
topology,
is
upper limit?
that is I'm going to do that. We will compare this topology with the topologies on R that we have defined in the lectures. Okay, so okay, so
Sir, sir, is 0, 1 difference k also in tau case?
so,
Because
sorry, can you speak little bit louder?
sir, 0, 1 difference k.
0, 1 minus k. Yes, by definition, right? It is
Yes,
open
sir.
interval and you subtracting k from this. Yeah. So comparison of tau k with other topologies on R. Okay, so first one is let's compare it with the usual topology on R. So what about tau k and tau e? So what do you think? Any inclusion or not comparable? Any guess? So just look at the definition. So what do we mean by comparability? So let X be a set and tau 1, tau 2 be two topologies. So how to compare this? So compare means tau 1 can be subset of tau 2 or tau 2 can be subset of tau 1 or they can be equal also. So in the first case, what do we call it? Tau 1 is coarser than tau 2 or tau 1 is smaller than tau 2. Now, can we make any comment about these two topologies?
Sir, tau k is finer than tau e.
Okay. Okay, so you are saying tau e is subset of tau k.
Yes,
Yes, so every element of tau e is element of tau k.
yes.
How to prove this? Just use the definition. So this is in fact true. So because you can see that open intervals, these are element of tau k. Open intervals is actually the basis of the usual topology. So if G belongs to, okay, so let's do this one at least one time so that you do not have any confusion. So let G belongs to tau e and we want to show G belongs to tau k. So how to show this? So now G belongs to tau e. This will imply for every element of G, you will find some Ax, Bx in R with Ax is less than Bx such that X belongs to this open interval Ax, Bx, and this is subset of G, right? So this is from the definition of usual topology. So this will imply G is basically union of these open intervals where X belongs to G. But these open intervals are element of tau k. Now since X, Bx, this is in tau k and tau k is a topology. So their arbitrary union is also in tau k. But their arbitrary union is basically G. So G is in tau k. So we have taken G from tau E and we have shown G is in tau k. So what we have proved? Tau E is subset of tau k. But can we say something more? So what we have is, in fact, tau E is strictly coarser than tau k. Okay. And why? So this is the first part and the second part. So note that this set, this is an element of tau k, and you can prove that this is not in tau E. So open interval minus 1 comma 1, and if you subtract k from this is element of tau k, but this is not an element of the usual topology. Okay, so can you see why it is not an element of usual topology?
So in usual topology, the only open sets are intervals.
Yes. No, not only open set, because union of open intervals are also there.
Hmm.
Yes.
Sir, because around zero we cannot form a neighborhood
Yes, exactly.
which is continuous.
Yes, exactly. So let me write down the reason here, because 0 belongs to this set, but if you take, but if there exist some real numbers with a less than b and 0 belongs to this open interval and this is subset of minus 1 comma 1, then we will get a contradiction. We will have a contradiction. And why? Because you see, 0 belongs to open interval a comma b. So that means a is less than 0 and b is greater than 0. B is positive real number. So by Archimedean property, you will find some natural number such that 0 less 1 by n less b. This is by Archimedean property. So you have to recall this from your uh, real analysis course. Right. So this 1 by n is inside. So this 1 by n is inside your open interval a comma b. But we are subtracting k from this. We are subtracting k, and k is consist of 1 by n. So that is not possible, right? So this will imply 1 by n belongs to minus 1 comma 1 minus k, and this is a contradiction. Okay. Any questions?
Sir, why not -2 to 1 open interval minus 1 by k doesn't belong to k topology, like that minus infinity open interval. Just if I take the only interval minus infinity to 1,
Minus
minus 1 by
infinity.
infinity,
Okay, wait. You are saying minus infinity to
1
1.
minus 1 by k. Why it doesn't belong to k topology? Or only minus 1 comma 1 minus 1 by k belongs to k topology.
Sorry, what is your question? I'm not
Sir, I
getting.
am asking, you said minus 1 open interval minus 1 to 1 minus 1 by k is the element belong to k topology.
Minus 1 to 1, and you are subtracting k. Why this is an element of the k topology?
Yes, sir.
Yeah, so you see the definition of k topology. So which subsets of G are in tau k? So for every element of that set, you have to find and either it has to satisfy this condition or this condition. So the second condition will hold. So now this element is in tau k. Why? So if you take any element from A, then you take A equals to -1 and B equals to 1. Then X is belongs to this set only, right? So this is your definition exactly, and this is sub equals to A.
Yes, sir. In a similar fashion, what happened in the minus 1 place if I put -2, just -2 or -3, like that, only just one element. If I -2 to 1 only.
-2 to 1, and you are
Okay.
subtracting K.
Yes, sir. Where
So
it
this
is
will also
contradicting
in
us.
that, this is also an element of tau K.
Means then I can say any interval minus infinity comma 1 means open at 1 with one interval or belongs to tau k.
Minus infinity 1.
Minus k.
Yeah, it is there.
Okay, sir. Yes.
Yeah, it is an element of tau K.
Okay, sir. That is. Thank you, sir.
Yeah, okay. Okay, any other questions? So we have compared K topology with the Euclidean topology. Now let's move on. Now let's compare the K topology with the co-countable topology. So this is the collection of all the sets whose complement is countable, right? That is the definition. So can we say something in this case? So recall what we have proved. From there it will follow. So what kind of sets in the K topology and what kind of sets are not in the K topology? So these two topologies are not comparable. These are not comparable. And why? So we have to prove two things, that tau k is not a subset of tau co-countable topology, and the other way, tau co-countable topology is not subset of tau k. So to prove the first one, we need to give a set which is in tau k but not in the co-countable topology. So can you give that set? So again, let me take that set itself. So this open interval minus 1 comma 1 minus k is an element of tau k, but it is not element of co-countable topology. It is clear, right? Because its complement is not countable. This interval is uncountable and you are subtracting a countable set. So what will be the complement of this set? So this will be R subtract minus 1 comma 1 and you take union with k. So if you see the real line and here is your 1 minus 1 to 1. So these elements and these elements are in this set in the complement. So this is the uncountable set. Okay. Now what about this part?
So the irrational numbers are in
Yes, exactly.
co-countable topology.
So R minus Q is in the co-countable topology, but it is not in the K topology that we have already shown. Okay. So these two topologies are not comparable. So maybe I will just draw that diagram that we already know. So the discrete topology is the largest topology on R, and if you take co-countable topology, also you can take lower limit topology, upper limit topology, and K topology. So this will be smaller than the discrete topology. And if you take the Euclidean topology, this will be strictly smaller than K topology, then upper limit topology, and the lower limit topology. But co-countable topology and Euclidean topology, these are not comparable. But if you take cofinite topology, this is strictly smaller than Euclidean topology and it is strictly smaller than the co-countable topology. And in the below we have the indiscrete topology. So this will be the overall picture. So co-countable topology and lower limit topology, upper limit topology, these are not comparable. That you can prove easily. So I am leaving that part to you. Okay, so try to remember this diagram. This is not difficult to see. This is useful because in many questions they give these topologies and say which is smaller than the other one or the other way. Okay, any questions? Okay, if there is no question, then let's move on. So maybe I will just write down the question. So if you see this diagram, and there is a question from GATE 2021. Now you can do this question easily. So let X be the set of all real numbers and consider the topologies on R. So tau 1 is the upper limit topology. Tau 2 is the cofinite topology. And tau 3 is the usual topology. Then which one is true? Option A is tau 2 subset of tau 3 subset of tau 1, tau 1 subset tau 2 subset tau 3, tau 3 subset tau 2 subset tau 1, and D is tau 2 subset tau 1 subset tau 3. Yeah, now can you answer this? Just look at the diagram. Okay. So tau 2 subset of tau 3. So cofinite topology is contained in usual topology, and usual topology is upper limit topology. Yeah, you are. Yes. So option is simply A, because tau cofinite topology is subset of tau Euclidean topology and it is contained in tau U. So this is your tau 2, this is tau 3, this is tau 1. Okay, maybe let's move on to some other kind of problems. Okay, so this is from GATE 2026. So let X be the set 5, 6, 7, 8, 9 and 10. Okay, and tau be a topology on X uh, defined as, so you have empty set, you have X, you have 5, 6, 7 and you have 8, 9, 10. Okay, so this is your topology on this set. Then the question is, then the number of subsets of X which are neither open nor closed. So what will be this number? So let's recall the closed sets. So if you have a topological space x comma tau, then a set a subset of X is closed if a complement means X minus A is an open set, means it is an element of tau. So complements of open sets are closed sets. That is the definition. So what is this question is saying? So they have given a set and they have given a topology on this set. They are asking the number of subsets which are neither open nor closed. So we need to find the total number of those kind of sets. So any idea how to do it?
60, sir.
Uh, yeah, but how?
Sir, since the set contains 6 elements, so total number of subsets will be 2 power 6.
Yes.
It will be 64. But the open sets here is empty set X and this one. And if we write a complement of this set, closed set also, again it will be the same set itself. So 4 sets which are both open and closed, remaining 60 are neither open and nor closed.
Okay. So basically what we are doing is, so what they have asked to count, we'll count exactly the opposite thing. So the number of neither open nor closed subsets of X is exactly equals to the total number of subsets minus the number of subsets which are both open as well as closed. Okay, so we need to count the complement. So which sets are both open as well as closed? So if you just see this topology here, in this case, to count this complement will be easier, because what will be the closed sets? So the closed sets are, so you just take the complements of the open sets. So complement of phi is whole set. So first I will write X. Complement of X is empty set. Complement of 5, 6, 7 is just 8, 9, 10. And complement of 8, 9, 10 is 5, 6, 7. So you have exactly 4 closed sets. And these are exactly the open sets. So these are both open as well as closed. So you have 4 sets. So these are the both open as well as closed sets. So the answer is cardinality of power set of X minus 4, and this is 2 power 6 minus 4, this is 16. Is it okay? Do you have any questions? Okay, so I hope you have got the idea. Okay, so the next one. So this is also from GET 2026. So the question is the number of distinct topologies on the set 1, 2, 3 consisting exactly 4 elements or 4 open sets. Okay, so we need to find the number of topologies whose cardinality is exactly 4. So maybe let's call this set as X. So we need to find the number of topologies tau on X such that cardinality of tau is 4. So is there any idea how to do it?
Just writing the four set topology
Sorry, sir.
consisting of empty set X and maybe singleton 1 and 2, 3, like that. It will be total 9.
Okay, so you just want to count it manually.
Means we have to write.
So, sorry.
Means we have to write all those what are the open sets are going to come.
Yeah, okay, but I think you don't have to do that much work. So let's try to see. So your cardinality of X is 3. So cardinality of power set of X is 2 power 3, which is 8. And what is your power set? Let's just write the largest topology. This is empty set. This is X. Now the singleton sets, then the double tone sets. That's all. Okay, so this is the collection of subsets of X. Now let tau be a topology on X such that cardinality of tau is 4, means tau consisting exactly 4 elements. Then let's analyze the structure of tau. So then what can be tau? So there are two obvious elements of tau, which is the empty set and the whole set. And suppose the other set is A and B. Right? Then if tau is this, then we need to find the number of choices for A and B. So phi and x are already in tau. So A and B can be come from these 6 elements. Right? So which elements can be? So if A is a singleton set and B is also singleton set, then their union also their union should also be in the topology, right? But their union cannot be in the topology because we have only 4 elements. So now note that similarly for double tones, note that A and B cannot be simultaneously singleton sets, because if you take two singleton sets A union B, then that will not be in tau because tau has only 4 elements. Now what happens if both A and B are double tone sets? Let's say 1 comma 2 and 1 comma 3. Now if you take their intersection, then that is singleton 1, but that is not in tau. So similarly, it cannot be simultaneously double tone sets. Also, AB cannot be simultaneously double tone sets because their intersection will not be in tau, because AB intersection AC, which is always non-empty, it is not in tau. So one of them has to be singleton and one of them has to be double tone. But those choices, all of them giving topology, that we have to check. So if you take 1 and if you take, let's say, 1, 2, then this is a topology because union is just 1, 2 and intersection is the smaller one. Similarly, if we take 1 and 1, 3, and if we take singleton 1 and 2, 3, then their intersection is empty and union is the whole set. So in fact, all of these choices will be topology. So the choices, so in fact, if A is singleton, then B has to be double tone or two element set. So the number of choices, so if you take A singleton, then there are 3 choices because 1, 2 and 3, and if you take B double tone, then 1, 2, 1, 3, and there are also 3 choices, so total 9 choices. So number of choices is 3 cross 3, which is 9, and you can in fact check that easily all these choices will be topology. So it is easy to check all these choices will be a topology on X. So the answer will be 9. Okay, so is it okay or do you have any doubt? Okay. Okay, so if it is okay, then let's move on. So it was problem number 8, problem number 9. So we have studied about basis for a topology, right? So if X is a non-empty set and B is a collection of subsets of X, then when we say B is a basis for a topology tau on X. So there the definition is, if you take a open set from tau, then G has to be union of members of B. So that is the definition. So every open set has to be union of the members of the basis. That is the definition. And we have seen one equivalent condition for a basis. So one thing, note that the elements of B, these are usually known as basic open sets. Okay, so we will usually refer this as basic open sets. Now let's see a problem related to basis. So this will be easier one. And after that, I will define a topology on the set of integers. That topology is important. And so many questions are there from that topology. Maybe I will come to those thing one by one. Maybe first let's do this one. So let B1 be a basis for a topology tau1 on X, and B2 be a basis for another topology tau2 on X. Now suppose tau1 is coarser than tau2, or tau1 is smaller than tau2, then can we say B1 is also smaller than B2? So is it true or false? So B1 is a basis for tau1, B2 is a basis for tau2, and tau1 is subset of tau2. So can you say something about the basis? Is it B1 is smaller than B2? Try to think.
I think this is opposites. Somewhere I read
Sorry?
that is the basis elements are contained one in the other, then the topologies will be oppositely contained. That is what I read somewhere in the MS.
No, but
Means
I am not
the
asking that.
statement is false from my side.
Okay, but why? Can you give some counter example or something?
Sir, this is a direct, I think a direct theorem. One theorem is there. When one topology is contained in the other, the basis element should be in opposite. Means if tau1 is contained in tau2, then the basis element B2 is contained in B1. In that format, I read one theorem that I remember, sir, but I forgot the example.
So you are saying if tau1 is subset of tau2, then B2 should be inside B1.
In that format, I read some theorems, but I am not
I don't
sure.
think it is true.
Okay, so in the
In what
next
you have
class, I
read,
will
it
rectify.
is in some different format, but this is not exactly that one. You will
Yes.
see that statement in the third week. So that will be comparison of topologies using basis elements. So you will see that. But for the timing, let's focus on this. if tau1 is subset of tau2, can we say b1 is subset of b2? So this statement is false. So one simple example. So you can take tau2, the discrete topology, right? Discrete topology is largest among all topologies. And for discrete topology, one basis is the singleton sets. Okay, so let x be your real number and tau1 let's be the usual topology, and let tau2 be the whole power set, means the discrete topology. So for tau1 you can take the open intervals as a basis, that we have already seen in the last lecture. So AB belongs to R with A less than B. So this forms a basis for the usual topology. And for the discrete topology, you can take all singleton sets. So then clearly tau1 is subset of tau2, because tau2 is the power set. It has to be subset. But b1 cannot be subset of b2, right? Even these two are not comparable in fact. So what you are saying, that you will also that is also not correct. It will be seen from this example. So did you got this example?
Yes, sir, I got it. Sir, why only for discrete topology? Why we are always getting singleton? I am not means how the open sets will look whenever I am going to for a discrete topology means for
Discrete
suppose if,
topology, every subset is open because it is the whole power set, right? So every
yes, sir.
element is in the topology, every subset.
Yes, sir. But when I take, for suppose if I take singleton one, singleton two, then the union should be also represented. That is one
Okay,
comma
so
two.
how this singleton sets forms a basis? You are asking that one?
Yes, sir. How it will?
Yeah, that is the
They,
usual trick. So if you take a subset, then you can write it as the arbitrary union of the singleton sets.
uh, yes, sir. The base of open sets will be union of basis element.
Yes, so it is
Yes,
arbitrary
right.
union.
Yes, I got it.
Okay, any other
Sir, can
questions?
you check the chat? Someone, I think someone has written some question. Is there any? I got a message like that.
So this is one of the questions on assignment one of week one. So which one? This one? Which question you are talking? Okay, maybe. So which question you are talking about? Okay, I think you're not. You're offline. Okay, maybe let's move on. So I will define a topology on the set of all integers, and I will again come back to that topology uh, in the next problem solving sessions, and that will be important one. This topology will be important one. Uh, So this is known as a topology or arithmetic progression topology on Z. Topology or a topology on Z. So if comes from Furstenberg, so who used this topology to give an interesting proof of a well-known result of infinitude of primes. Maybe I will come to that later, but first let me define it. So maybe I will introduce a notation first. So for A, B belongs to Z with A positive, let's denote this set AZ plus B. So AZ plus B means just AN plus B, where N is running over the integers. Okay, so this is one set. So more particularly, this is just B, A plus B, 2A plus B, so on, minus A plus B, minus 2A plus B, and so on in the negative side. So this will be AZ plus B. Now using these sets, I will define a topology on Z. So define tau as those subsets of Z such that for every element of Z, there exists A belongs to Z with A positive such that AZ plus X is subset of G. Okay, so this will be my definition of a topology. So all those subsets of Z such that if you take a element from that, sorry, this is G, not Z, such that for all X belongs to G, you will get a corresponding positive integer such that this set AZ plus X is inside G. Okay, I hope the definition is clear. So I can prove that it is a topology. It is not a difficult task. Maybe let's do it quickly. Then tau is a topology on Z. This is known as a topology or arithmetic progression topology on Z. Maybe let's prove this. The empty set and the whole set is clearly there. So empty set and whole set Z, it will be there. It is just trivial. Now prove that the finite intersection axiom. So so I will do it for 2 because it is equivalent. Let's 2 element from tau, and I will prove that their intersection is in tau. So we want to show G1 intersection G2 is in tau. Now if G1 is empty or G2 is empty, then their intersection is empty and it is in tau. So let none of them are empty sets. Okay, so we have to prove their intersection is in tau. So let X be an element from the intersection. So this will imply X belongs to G1 as well as X belongs to G2. So by definition, there exist two positive integers a1, a2 such that a1z plus x, this is subset of G1, and a2z plus x, this is subset of G2. So what we have to prove is we have to show there exists some a positive such that az plus x is subset of G1 intersection G2. Right? This is what we want to prove. Now, can you guess uh, how to do this?
Sir, the LCM of A1 and A2.
Yes, but even if you take just the product, that will also work. So let now claim a1 a2z plus x is subset of G1 intersection G2. Yes, LCM is the best choice, but product is enough. So let's prove this containment. So let's take an element from the left hand side. Let's say it is R belongs to a1 a2z plus x, and we need to prove that R is in G1 intersection G2. So R is in this set. So by definition, R equals to a1 a2 times some n plus x for some n. Now this you can write it as a1 times a2n plus x, then it is belongs to a1z plus x subset of G1, or you can write this as a2 times a1n plus x, and this will belongs to a2z plus x, and this is subset of G2, but this is the same element. So R belongs to both G1 intersection G2. So this will imply G1 intersection G2 is in tau. So tau is closed under finite intersection. Is it okay? Okay. Now the closed under arbitrary union. So let Gi such that I belongs to this index set I be okay such that Gi belongs to tau for all I is in tau. We want to show the union Gi such that I belongs to I is also in tau. So let's prove this by definition. Let's take an element from the union. Let's take X belongs to this union. So then by definition X belongs to some Gi for some I, but Gi is an open set. So this will imply there exists a positive such that az plus x is subset of Gi. So this implies this Az plus X is subset of Gi, and this is subset of the union. So this union has to be an element of tau. So this part is fairly easy. So tau is a topology on Z. So is the proof clear?
Yes, sir.
Yeah, okay. So now this topology has many interesting properties. Maybe I will mention some properties for the time being now. Okay. And you might see questions in the exams like GATE or other exams from this topology. And also it is interesting. So so maybe first mention one this that this Az plus B, this is an open set. This is open as well as closed. This is open set as well as closed set. So this Az plus B is open. This is clear from the definition itself, right? So Az plus B belongs to tau is clear from the definition. But why it is a closed set? Can you say? Can you guess? So what about the complement of this set? So what is Z minus Az plus B? So you can check that this set is precisely the union of Az plus B plus I, where I is running from 1 to A minus 1. So these are open sets, and this is union of open sets. So union of open set is open. So this I am leaving this as exercise, but it is very easy. You just have to prove the containment of each side. Or there is other way to do this also, but I'm not mentioning it now. Now this is an open set. So complement is open. So this will imply this is closed. Okay, so these sets Az plus B are both open as well as closed. So this is the first property. Now the second one. Second one is no finite set is open. No finite subset of Z is open. Now this one is very easy to see. Can you tell me why this one is easy?
Because otherwise it would contain an infinite set.
Exactly. So this Az plus X, these are infinite sets. Uh, so if A subset of Z is finite, Oh, but it has to be non-empty because empty set is already there. Then az plus x cannot be subset of A, right, for any A positive, because az plus x is an infinite set. So from the definition of the topology, finite sets cannot be element of the topology. Okay. So now using these two facts, I can prove what I told, that proof of infinitude of primes. And because of this thing, this is known as F topology. It was proved by Furstenberg. So what does it mean? So I want to prove the number, if you take the set of all prime numbers, then that is an infinite set. So that we want to prove by using this topology. So we want to prove the set, or maybe prime numbers are infinite, or maybe there are infinitely many prime numbers. We want to, sorry, we want to show that there are infinitely many prime numbers. Okay, so let's do this. How to do this? So first thing to note that no finite set is open, right, by the second property. So minus 1 comma 1 is not an open set by property 2. So this implies its complement cannot be a closed set. So z minus 1 comma 1 is not a closed set. This is the first thing. Now the second thing is, what is this set? Can you identify this set? So this set is basically union of all pz, or pz plus 0, or just pz, let's not mention 0, where p is a prime number. So let's prove this. Why this is true? Can you see why this is true?
Because every um, uh, integer of modulus greater than or equal to 2 has a prime divisor.
Yes, exactly. So this containment is clear. This is trivial. Now to prove this one, uh, observe that every integer other than plus minus 1 has a prime divisor. So if you take n belongs to z minus plus minus 1, then there exists P such that P divides N. So this will imply N belongs to Pz. So this set is exactly union of this Pz. And by our first observation, this set is not a closed set. But what we know, this Pz is closed set, right? By the first property. This Az plus B are closed sets. So Pz's are closed sets. So what will happen if there are only finitely many prime numbers?
Finite union of closed sets is a closed set.
Yes. So if there are finitely many prime numbers, then this is a finite union of closed sets. So this has to be a closed set. That is a contradiction. So if there is there are finitely many prime numbers, if there are only finitely many prime numbers, then this union Pz, where P is prime, is a finite union of closed sets. And that implies Z minus plus minus 1 has to be a closed set. So this is a contradiction. So there cannot be finitely many prime numbers. This implies there are infinitely many prime numbers. Okay, so this completes the proof. The proof is fairly easier. You just have to do it step by step. So we'll come to this topology later with some other problems maybe. Uh, okay, so far any questions or queries?
No, sir.
Okay. Uh, if do you have any doubt, you just post it to the discussion forum, or maybe you can ask it in the next live sessions also if you do not have any now. It's already 7:55. Okay, so if you do not have any questions, then maybe we'll stop this session here.
Yes, sir. Thank you, sir.
Yeah, okay.
Thank you, sir.
Okay, see you all in the next live session.